This is the sound of a quantum computer.
Sounds absolutely nuts.
Unlike anything you've seen before.
Quantum supremacy.
Sounds a bit sporty.
Controllable randomness.
Both 0 and 1 at the same time.
Dental floss.
An oven with calcium inside.
Cryogenic refrigerator.
Electrons sloshing around.
Dental floss.
There's a parallel universe in which you're indeed a rock star.
Going to the moon.
In particle physics labs all over the world, people are trying to perfect quantum computers.
They're a new type of computer that exploits the unusual laws of quantum physics to work faster and frankly weirder than anything on your desktop, and they could be the start of something truly revolutionary.
Like many world-weary rationalists, we've been contradictorily praying for some miraculous technological fix to civilization's most pressing crises. Environmental destruction, famine, disease.
Constant buffering on Netflix.
And now we could be on the verge of finding that fix.
What, just for the buffering or for the survival of humanity stuff as well?
Shh. I'm Jim Mortleman, professional tech scribbler and all-purpose word tinkerer.
And I'm Stuart Houghton, writer, IT geek, proud owner of a D in A-level physics.
And this is Stupid Qubit, quantum computing for the clueless, where we'll be trying to find answers to all our dumb questions about a technology that's got us more excited than anything since Space Invaders.
Questions like, what exactly is a quantum computer? And will I be able to make one using parts I got from the Mapping clearance sale?
Do they really work across parallel universes? And if so, how do we know we're in the universe where they give us the right answers?
How do you program one and what games will it run?
Are they on the verge of cracking all our encrypted internet communications? And what difference will it make if I delete my web history now?
Who's funding the technology? And should we be worried if they have Analytica in their name?
Are we really on the verge of quantum supremacy?
What is quantum supremacy?
Does it mean these machines will attain consciousness and wipe out the human race?
Or figure out the meaning of life and save civilization?
And when will we get our conscious, intelligent, matter-manipulating quantum smartphones? Hello and welcome to the first episode of Stupid Qubit, where we'll be asking what the photonic muck is a quantum computer.
And when will we get one?
Now! But it can't do very much yet, about which more later.
As well as meeting some of the key scientists in the field, we'll also be talking to the man in the pub.
And not just any man in the pub, but the pub landlord Al Murray, who will be giving the chance to ask some quantum questions. Anything he wants about quantum computing.
That's coming up in a bit. Anyway, when we recorded the preview episode of this podcast, we said we reckoned the infinite improbability drive in the Hitchhiker's Guide to the Galaxy,
which passes through every conceivable point in every conceivable universe simultaneously when it reaches infinite improbability,
was the world's first quantum computer in fiction.
Well, since then we have seen and touched one of the world's first quantum computers in fact. It's called IBM Q, and it's the thing you heard in the theme tune just now, jangling and hissing like an armoured Morris dancer on a punctured space hopper.
And it does indeed exhibit striking similarities to the infinite improbability drive, except that, while that, you might recall, was powered by a nice hot cup of tea, this is powered by a nice cold flask of chips. Well, a flask of chip. Anyway, here's me taking my very first peek. So I'm here with the IBM Q, which is it's an actual quantum computer, and I mean from here it looks like something you'd find in the middle of the TARDIS. It's this bizarre lampshade kind of chandelier contraption. There's wires and coolant tubes and copper braiding, and it really is just the most bizarre looking piece of hardware. The actual computing bit is a tiny cylinder at the bottom, which they've just removed, and inside there's a really nondescript metal rectangle. That seems to be the actual business end. And the rest of it is just this baroque... it's like something you'd find at the end of the Great British Bake Off if they're doing sugar sculpture. It's just incredible.
Full disclosure, it wasn't actually on and working when we saw it.
Well, it had only popped over to the UK for a quick holiday, and who does any work when they're on holiday?
Using the magic of technology, we just dubbed on the recording of the sound it makes to give you a more visceral listening experience.
So what you're saying is it's all smoke and mirrors?
No, copper, steel, wires, superconducting metal, cylinders, plates and dental floss.
Dental floss?
Dental floss.
That was Dr. Jerry Chow, who heads up the experimental quantum group at IBM Research. He'll be telling us a bit more about that later, as well as why IBM's quantum computer looks like a steampunk chandelier and sounds like a bicycle pump having sex with a typewriter.
But the reason we're so excited by all this brilliantly mad science is that if it works, it could herald a wave of discovery and technological advancement the likes of which humanity has never seen.
Within months, a quantum computer might, for the first time, solve a problem faster than the world's most powerful supercomputer. Within a few years, we could be using them to design new drugs, chemicals and smart materials with potentially world-changing properties.
And within the lifetime of people today, they might enable us to accurately model complex systems like the weather, molecules and the human brain, ushering in true artificial intelligence, providing solutions to many of humanity's thorniest problems, and giving us fundamental insights into our existence and the nature of the universe.
Or they might not, but we wanted to know more, so we decided to quiz the people who understand what it's all about.
On behalf of all of us that don't, which right now is pretty much everyone, and most definitely us.
As well as IBM's Jerry Chow, we'll be meeting
Simon Benjamin, the Professor of Quantum Technologies here at the University of Oxford.
who, among other things, will tell us if quantum computers really work in parallel universes, and what they've got in common with smartphone camera envy.
We'll also hear from
John Martinis, head of the quantum hardware team for Google.
who believes quantum computing is the new space race. He tells us why he thinks he's set to achieve quantum supremacy, what exactly that is, and whether we'll soon have to submit to his army of quantum robot overlords.
Spoiler, we won't.
You can't know that for sure.
I can. The type of quantum computer Google's making only works at just above absolute zero, which confusingly isn't zero, it's minus 273 degrees centigrade. So, unless the Earth's about to enter some kind of hyper ice age, it's going to have a bit of bother enslaving humanity.
If you say so, but don't come crying to me when your pale, withered body is submerged in jelly with all wires sticking out of it like in the Matrix. A nightmarish cyber dystopia isn't the only possible future for quantum computers. They could eradicate diseases, fix the environment, feed the world, and usher in an age of global peace and prosperity for all. Subject to terms and conditions, always read the small print.
We're getting a bit ahead of ourselves here. Before we start guessing how these things are going to transform our lives, we should maybe explain what a quantum computer is, and why it's so different from the laptop on your desk or the phone in your pocket.
Good idea. I mean, it's bigger for one thing, and you don't need to cool your phone to minus 273 degrees.
True, but the main difference is to do with how they store and process information. A regular computer uses binary digits or bits to represent information, and each bit can either be 0 or 1. And now normally we count in decimal, which is based on multiples of 10. Take the number 101. In decimal, those 3 digits are telling you need 100 plus 0 tens plus 1 unit, so that makes 101. Each column to the left is worth 10 times the one to its right. So after the hundreds, you have a thousands column, then tens of thousands, then hundreds of thousands, and so on.
Are you making another bake-off illusion?
Hundreds of thousands, not hundreds and thousands. Anyway, in binary, because you have 2 digits and not 10, each column's value is twice that to the one on its right. So 1, 2, 4, 8, 16, 32, and so on. So the digits 101 in binary are telling you that the number is worth 1 4 plus 0 2s plus 1 unit, so 5.
Well, thanks for that excellent 5.
Hey?
Excellent 101 in binary. For someone used to counting on 10 fingers, it might seem a bit long-winded, but it's really handy for computers because they can represent the ones and zeros of binary numbers inside electronic circuits as ons and offs. A computer's brain or processor is effectively just a load of switches connected in a way that lets it store and manipulate binary numbers. A quantum computer works in much the same way.
Except completely different. In fact, let's back up a bit. Before we ask what a quantum computer is, maybe we should be asking what the freaky fleck is a quantum anything.
Well, Nobel Prize-winning quantum physicist and the spiritual father of quantum computing, Richard Feynman, once said,
"Things on a very small scale behave like nothing that you know about."
This is going to go well. Okay, I'm going to try and remember the really confused explanation of this that my A-level physics teacher gave us.
Hit me.
Basically, the kind of physics you learn in school is what we might call classical physics. It's all the laws that govern how the universe works, like force equals mass times acceleration, which is Newton's law of motion, or what goes up must come down, which is Newton's law of
Internet censorship.
Gravity, or E equals mc squared, or the laws of thermodynamics.
Which are?
Energy can't be created or destroyed, the entropy of a system always increases. Just Google it. The point is, they're fairly solid and well understood, and for a time, physicists thought they had pretty much everything figured out. I mean, okay, there are always going to be more things to discover, but the universe seemed to work like clockwork. If you knew all the variables, you could predict precisely how it would behave.
And then some plank gonna done a quantum.
Exactly. Wow, it's like Stephen Hawking's in the room. Anyway, it all started to go a bit wrong about 100 years ago when scientists began to investigate what goes on inside the atom, the so-called subatomic or quantum mechanical world.
Right, starting with some Planck, Max Planck, who discovered weird particles of light that didn't obey the usual laws of physics, which he called quanta, hence quantum physics. And I've read enough popular science articles with cartoons of cats in boxes to know this is where things start to get interesting.
Yeah, basically, all those classical laws of physics, it turns out they're not really laws after all. They're more like district advisory codes. They're only applicable to things bigger than an atom. Inside the atom, meanwhile, there's a whole lot of weird shizzle going down. Things that exist in more than one place at the same time, particles that teleport, particles with an eerie, constant connection across space and time.
Cats in boxes that are both alive and dead at the same time?
We interrupt this podcast to bring you a word from our sponsor.
Schrodinger's cat boxes are ideal for a cozy cat nap or a trip to the vets. Use the code Qubit to get 50% off your first order. Your cat has a 50% chance of survival. May contain decaying radioactive material.
Actually, Schrodinger's cat was a thought experiment to illustrate one principle of quantum physics that's really important to quantum computing, that of quantum superposition. The idea that at a subatomic level, things can exist in two or more different states simultaneously.
You mean like if you stand on the border of two countries with one foot in each, like North Korean leader Kim Jong-un did when he met the South's president?
Not exactly. But since getting your head around quantum physics means entertaining concepts like parallel universes, or the idea that matter only becomes solid when you look at it.
Or if you're Elon Musk, that we're already living inside a quantum computer simulation.
And that, yeah. So anyway, I guess that if some despotic East Asian leaders' border-straddling photo-op antics help you to better make sense of all this quantum craziness, then in some ways it's an okay analogy. Although here's Jerry Chow of IBM with a better one.
The whole concept of superposition is actually not so difficult. When you flip a coin, it's in a superposition of 0 and 1, right? But there's also what's known as a quantum superposition. Quantum superposition is still kind of like that coin. There's a randomness part of it, where you're kind of in the case of a coin, you're kind of in heads and tails at the same time.
Okay, so superposition is like a coin in mid-toss, but what's all this about parallel universes? Here's Oxford University's Professor Simon Benjamin.
So, the funny thing about quantum physics is we understand the maths of it completely. And the maths allows us to tell what will happen when we do an experiment, or if we had a computer, it allows us to understand what comes out of it. But we don't really understand what quantum physics means about the universe. It's as if someone has given us the rules, but we don't understand what the underlying meaning of it all is. So what people have done, philosophers of physics, is they've come up with a few different things it might mean, which are called interpretations of quantum physics. And one of them is the one you mentioned, which is parallel universes. Maybe the reason it seems like things can be in two or more states at the same time is that in one universe it's in one situation, and in one universe it's in a different state, and there are parallel universes. That's one interpretation of the maths, but there's no way that we found so far to tell whether that's the right picture of what it all means, or if there are some other explanation. So is it really going on in different parallel universes? We don't know. It's quite fun to talk about, and everybody loves to imagine that there's a parallel universe in which, they're a rock star or something. In fact, there's a parallel universe, according to that theory, for every possibility. So there is one in which you're indeed a rock star, and there's one in which you're an arch criminal, and so on.
Okay, so that's quantum physics sorted then. It's like Feynman said, this stuff seems peculiar and mysterious to everyone. Still, since we wouldn't have lasers, GPS positioning or MRI scanners without it, among other things, the theory's clearly sound. So let's get back to how this weird physics can help us build an insanely powerful computer that's like nothing we've seen before.
Okay, well, hold that thought about quantum superposition, because instead of the bit, the basic building block of a quantum computer is the quantum bit, or qubit. The weird thing about a qubit is that it can be both 1 and 0 at the same time. Here's Simon Benjamin again.
Roughly speaking, all computers that we have today, from your phone through to the biggest supercomputers, basically work in the same sort of way. They have transistors in them, and those are little gadgets which can either be in what we would call state 1 or state 0. So they're very good at storing zeros and ones inside themselves, and that's how all the information and all the movies and everything that we process with computers works. Now, that's not the only way to do it. That's just the way that has worked out really well for us so far. And in fact, nearly 30 years ago, it was realized that if you look at what physics will let you do, you can do something much stranger and maybe more powerful. You can use the fact that physics is at the lowest level, based on quantum mechanics, and that allows you to do some strange things like be in two places at once or two conditions at the same time. Sounds crazy to us. Sounds just absolute nuts, but it is the way things work down there, and you can build a computer based on that kind of principle, based on, instead of the bit, which is famously a 0 or a 1, on a quantum bit, which is called a qubit for short, and it can be 0 and 1 at the same time. Very strange and very difficult to do, but we're now pretty much on the verge of doing it, and we shall see if these strange new kinds of computer are, as we hope, much more powerful.
So a qubit can be 0 and 1 at the same time. Why is that such a big deal? Here's Professor John Martinis, head of the quantum team at Google and architect of what's arguably the most powerful quantum computer in the world today.
The big deal is that as you make more quantum bits, then the amount of parallelism goes up. So if you have 2 qubits, you can process 0, 0, 0, 1, 1, 0, 1, 1 at the same time, or 4 states. And if you have 3 qubits, it's all combinations and 0 and 1s for 3 elements, and that's actually 8 states. So every time you add a qubit, your parallel processing power increases by a factor of 2. So 8, 16, 32, 64, 128, etc., as you increase the number of qubits. And this parallel processing is going up exponentially with the number of qubits. So by the time you get to something like 50 qubits, the parallel processing power is kind of like the size scale of a supercomputer, let's say the memory of a supercomputer. And then by the time you're up at about 300 qubits, that number is the number of atoms in the universe. So clearly you could never build a classical computer that could have that parallel processing power. Quantum systems are fundamentally very, very powerful as a parallel processor because of that.
Parallel processing means doing different calculations all at the same time. Computers can do parallel processing to a certain extent, and supercomputers are really good at it because they have lots of processors linked together running simultaneously. But there's a physical limit to what they can do. And if you want to double their parallel processing power, you have to double the number of processors they contain. But what the professor is saying is that every time you add a single qubit to a quantum computer, you double the number of calculations it's able to process in parallel. And as any ruined gambler knows, if you keep doubling up, you're very quickly going to get into very big numbers.
It's like the legend of the man who invented chess. According to the story, the inventor presented his game to the Emperor of India, who loved it so much he asked the man to name what he'd like as a reward. The man said all he wanted was 1 grain of rice for the first square on the board, 2 grains for the second square, 4 for the third, doubling the number of grains on each square up to the final 64th square. Thinking this a modest request, the Emperor agreed. In fact, he would have needed 18.5 quintillion grains to give the man his promised reward.
Quintillion?
A 1 with 18 zeros on the end. In other words, about as much rice as you could grow if you used all the fertile land on the planet for nothing but rice production for several hundred years.
He must have felt a right nugget.
It's okay, he was the emperor, he probably just had the bloke killed.
Right, so the point of the story is, don't be a smart ass? Or that a 64-qubit computer could process quite a lot of numbers at the same time, quite possibly in quintillions of parallel universes.
Exactly. If you had a quantum computer with 64 qubits, you'd have already surpassed the world's most powerful supercomputers and would probably have your sights set on making enough additional qubits to start reversing global warming or creating the Matrix.
Hang on. How many qubits has Google's new quantum computer got? The one you said that was arguably the most powerful in the world.
72. In a chip called bristlecone, which, like IBM's, only works if you sit it in a steampunk superfridge.
Well, job done then, surely. That's way more than the 50 qubits the professor said was needed to surpass today's supercomputers, so why hasn't it taken over the world yet?
Because to realise the kind of computing power that Professor Martinis is talking about, your qubits have to stay connected and in their weird states of superposition long enough to do a complex calculation, and without making errors that corrupt the results. And so far, no one's managed to get them to do that. Here's Simon Benjamin again.
What that comes down to is that qubits, when we build them in the lab, don't behave very well. It's very difficult to make them do exactly what you want them to do. So we can think of them as suffering errors or having noise. And getting rid of that or dealing with it is really the real trick to building a quantum computer successfully.
So when someone tells us their quantum computer is better because it's got more qubits than the next guy's, we should take it with a pinch of salt, right?
It doesn't matter how many qubits you've got. If the noise levels are such that you can only do 10 things before everything is collapsed, adding more qubits won't help. It's a bit like mobile phone cameras. There was a time when the only thing anyone could talk about was how many megapixels their camera had, right? And, down the pub, you'd be like, oh, mine's got 4.6 megapixels. And the other guys, well, mine's got 5.4. Now, I actually know someone, an ex-student of mine, who works in the industry trying to produce the next generation of phone cameras. And it's very frustrating for the engineers because they know it's not always more pixels that will make things better. Sometimes the optics needs to improve or other aspects of it. But it's tough to explain that to the general public. And similarly for quantum computers, the number of qubits is super important. And you will never have a powerful quantum computer without a good number of qubits. But it's not the only thing. And the second ingredient, which I think everyone can try and understand, is how well behaved your qubits are. What is the noise level? And if it's too high, then adding more qubits won't help. Just like in a mobile phone camera, if the optics is rubbish, you can double the number of pixels in there, and it won't make nice photos.
So the people building these machines are using various techniques to correct for errors, including bundling several qubits together as a single qubit, so there are multiple fail-safes for the ones that don't work properly. In fact, estimates as to how many of today's qubits you'd need to produce just one properly error-corrected qubit range between 1,000 and 1,000,000 depending on who you ask, and you'll probably need upwards of 1,000 of these well-behaved qubits to build the kind of universal logical quantum computer that everyone's aiming for.
But it seems there may be some pretty useful things we can do with these machines even before we get perfect qubits, and the field is moving far more quickly than even many at the heart of the endeavour believed possible a few years ago.
So, how do you make a quantum computer? Well, once you've built your qubits, you need to connect them together using another spooky principle of quantum physics called entanglement. Here's Jerry Chow again.
Entanglement is just a very special kind of superposition, where if you have multiple quantum objects entangled, there's actually more information contained in the fact that they're together and they're entangled and correlated than if they were separated apart and you were to look at them individually. So there's more in the whole than there is in the individual parts.
Which accounts for the exponential doubling Professor Martinis was talking about. Now, you might be wondering what the problem is with entangling and controlling ever more qubits.
The problem is, qubits are very fragile. They're extremely sensitive to environmental factors like temperature, vibrations, magnetic fields, scientists trying to control them, and so on. That's the noise Simon Benjamin was talking about. As a result, qubits can't hold their state of superposition for very long before they fizzle out, or decohere to use the scientific terminology, and that means they're prone to lots of errors. Not only that, but the more qubits you try to hook up, the less reliable they become, because every time you connect more stuff to your system, you create even more noise.
So, although we're starting to see quantum computers with upwards of 50 and soon upwards of 100 qubits, they can't yet be entangled in a way that lets them do the really useful things we hope to be able to do in the not too distant future. As you try and scale these things up, they become prone to ever more errors.
In fact, at the time of recording, the largest number of qubits anyone's managed to entangle successfully is 18. That was reported earlier this summer by a team in China led by the country's top quantum physicist, Pan Janeway.
Janeway? Like the captain on Star Trek Voyager? That's surely a sign.
Well, Voyager was one of the weaker Star Trek franchises, so maybe it's a sign things aren't all going to go China's way. And they'll have to successfully entangle a fair few more than that if they're going to decrypt all the West's secret data.
There's also a quantum computer made by D-Wave, a Canadian company, that has over 2,000 qubits.
But you definitely can't compare theirs to the logical, general-purpose quantum computers that the big players are trying to perfect. D-Wave's machines are the fruits of a connected but significantly different discipline called adiabatic quantum computing, which we hope to explore in a future episode.
Adiabatic quantum machines are even less like classical computers, in that they don't even try and replicate the logical circuits needed to build a universal problem-solving device, but apparently they are quite good at helping with a very specific branch of calculations that classical computers have traditionally struggled with.
Combinatorial optimization problems, they're called, those where you need to find the optimum arrangement of a finite set of given data. Things like discovering the shortest circular route a travelling salesman can make in order to visit all the towns on his list.
So now all of our listeners are wondering how these machines do calculations like that without performing any logical computing operations.
As are we. No one's yet managed to explain adiabatic quantum computing to us in a way we can understand. Although if anyone fancies a go, do please get in touch and offer yourself up for dumb questioning.
We know it uses a technique called quantum annealing and that it has something to do with measuring low energy ground states, whatever they are, Possibly something to do with twiddling dials like on an analog synthesizer, but frankly, towards it all sounds a bit Noel Edmonds.
And as far as we can tell, no one has yet proved these adiabatic quantum machines, with all their qubits sloshing around willy-nilly like some quantum minestrone soup, can do anything that can't be effectively simulated on classical computers.
That said, as well as the main effort to build a logical quantum computer, Google also has a finger in the adiabatic pie. Not only that, but Japanese tech giant Fujitsu recently announced a classical chip called the Digital Annealer that was inspired by D-Wave's machines, so let's not write off this adiabatic stuff yet. But what we're really interested in is how you build a quantum machine that makes classical computers look like an abacus. The kind of machine with perfectly performing entangled qubits that don't throw up any random errors, and that's the kind of machine we're going to need to perform these mind-boggling feats of split-second problem solving that you need to do all the really impressive stuff like curing cancer, or ending global warming, or devising a workable Brexit plan. So how long is it going to be before someone gets there?
To a workable Brexit? I don't think even the infinite improbability drive could solve that one. But as to when we get a machine that can do the easier stuff, like curing cancer, the average estimates coming from the scientists involved have halved over the past few years, from, ooh, they won't be here for at least 30 years, to, we could have them within 15. Microsoft reckon they might be able to do it in under 10. The honest answer is no one knows exactly, but people are trying all sorts of madcap ways to get there. Different groups are working on different techniques, using different materials to build their qubits, experimenting with different ways of connecting and controlling them, but it's essentially now an engineering challenge rather than a theoretical one.
And in the past couple of years, there's been a sharp influx of investment, a sharp acceleration in quantum engineering breakthroughs, and a distinct sense of excitement among the quantum computing community that we're on the cusp of a new phase where these machines can open up exciting new possibilities to do some truly world-changing science.
There are around 50 credible, well-funded projects across the world that have built or are in the process of building quantum computers. As well as activity among academic institutions, governments and startups, many tech giants are involved, including IBM, Google, Microsoft and Intel in the US, and leading Chinese web companies such as Alibaba and Baidu. It's like the Wild West out there.
Or maybe the Wild West and the Wild East at the same time.
Google's John Martinis even sees the international competition to build a large-scale quantum computer as akin to a new space race. So, does he think we're in orbit yet?
Yeah, so the analogy I use of the space race is because there's a huge number of people trying to build a quantum computer. You have large national programs doing this. You have private companies, a lot of academic and non-academic groups. There's a lot of different ways that people are trying to do this. So it's an exciting time. I don't think we're quite into orbit. I think we're starting to launch sounding rockets right now that are taking off and going, significantly up into the air. But I don't think we're even in orbit. We're still working on building a powerful enough system to do that. Some are maybe working on a more complicated technology, so it's harder to build the first rocket. But, if they get it to launch and get it to work right, then it's going to go farther, potentially. So we just have to see which of the ideas are working well.
So if we're just getting into orbit, what's it going to take to reach the moon?
I'm going to say going to the moon is doing a really complex problem that is useful and solves a problem that we're interested in. Let's say I'm going to give an example where we solve a quantum chemistry problem for some very complex molecule. So that's kind of going to the moon, doing something useful.
Now we've got loads more questions, but it's all quite a lot to take in, so this is probably a good point to pause and introduce the slot we're calling
Quantum Questions, Quantum Questions, Quantum Questions.
We're sure we're not the only ones who are burning but probably quite dumb questions about this emerging technology, and we want to give you the chance to ask yours. Tweet at StupidQubit or email hq@stupidqubit.com, and we'll choose the stupidest questions each time and do our best to answer them semi-seriously.
And if we can't,
which is far more likely,
then we'll put them to the scientists building these things, because we found that more often than not, the dumbest questions can lead to the most fascinating answers.
And as it's our first episode, we thought we'd try and seek out a special guest to ask the inaugural
Quantum Questions.
So we ventured down the boozer to collar the quintessential man in the pub.
Confirmed quantum clueless clot, Murray the Pub Landlord. So Al, did you know that scientists may be on the verge of making quantum computers that can do insanely complicated calculations in a split second by trying out all the answers at the same time, possibly in zillions of parallel universes?
No, you're making it up. That surely doesn't exist.
Well, not quite, but the early prototypes are showing promise, and it might not be too long before these things overtake the world's fastest supercomputers. We're sure you must have a question about the technology that holds such revolutionary promise for the advance of civilization.
Well, I've seen that James Bond film, Quantum of Solace. Is it anything to do with that?
I suppose James Bond does have to make lots of split-second calculations, and he's always entangled with some Bond girl or other when getting into superpositions. Essentially, though, no, nothing to do with that. But ask another one.
Is it like mucky pictures, internet style?
No.
Does it mean the videos load quicker? Does it mean that?
Well, we watched a TED talk the other day with a scientist called Stefan, who's trying to build the quantum internet. And while she didn't say it'd be faster, she did say it would be completely private, secure and unhackable. So it'd allow someone to watch the mucky stuff, safe in the knowledge that no one else would know what they were up to. But that's the loading faster, sorry.
No. Okay.
Well, having said that, one of the key areas where quantum computers are showing signs of promise is in designing new smart materials. So they might be able to help us invent cables that can carry more data, which will result in fewer internet bottlenecks, hence faster loading times.
Yeah, and with the insanely powerful machines they're hoping to perfect not too many years from now, who knows, they might even fathom out a way to send the videos directly to your cerebral cortex, with all the sensations too, a bit like in Videodrome or Total Recall.
Sounds well beyond my my intellectual grade. Good luck to them though, if they think they can make that work.
Many thanks to Al Murray there. Now, back to qubits and how the quark you go about making them. Well, there are lots of ways, but in this episode we're going to focus on the approach that's so far borne the most fruit. The state-of-the-art research and commercial machines with 50 or more qubits that are starting to appear from the likes of Google, IBM and others who make their qubits from superconducting metals.
A superconducting metal is one that, when cooled to extremely low temperatures, can transport electrons with no resistance, which means that they don't release any heat, sound or any other energy that can interfere with the quantum weirdness that you need for them to work. The first company to successfully build a quantum machine based on this technique and make it available for anyone to play with on the internet was IBM, which launched a 5-qubit quantum computer in the cloud more than 2 years ago. They've now got a 16 and a 20-qubit one online, plus the one they showed us, which has 50. And there's a new one in the pipeline.
By the way, any non-techie millennials listening whose knowledge of technology begins and ends with the iPhone might be surprised to learn that IBM was the original tech giant.
Apple, incidentally, hasn't yet announced any plans to build a quantum computer, but if it did, no doubt it would be twice the price of all the others, use a different plug, and have to be cooled with special quantum ice you can only get in the mountains of Tibet.
Yeah, it'd be the prettiest though. But back to IBM. Formed in 1911 as the Computing Tabulating Recording Company, it changed its name to International Business Machines, or IBM, in 1924 and dominated computing through most of the 20th century. It's always been at the cutting edge of new developments, as well as popularising the mainframe and inventing the PC. In 1996, its supercomputer Deep Blue beat Grandmaster Garry Kasparov at chess. In 2011, its AI Watson won the US TV quiz show Jeopardy! And one of its scientists, Charlie Bennett, was talking about using quantum systems to process information several years before Nobel Prize-winning physicist Richard Feynman first proposed a basic model for quantum computers in 1981.
So could this company's superconducting quantum computing efforts propel it back to the very top of the tech league table? Here's Jerry Chow.
There's still some dark arts to understanding how to make better superconducting qubits. The entire field is ripe with exploration of different types of superconducting materials. You see people using aluminum, niobium, tantalum, titanium nitride, all kinds of different metals that are superconducting, and people are still actively investigating what's better, what kind of fabrication processes make them work better, how do we design the circuits better to have less noise and longer coherence. There's definitely a lot of interesting efforts going out on all these different qubits, and they can all be susceptible to different types of noise and errors, and so how they all perform as we scale up is still something to be seen. With superconducting qubits though, we've seen this tremendous progress in our community pushing forward on coherence, controllability, and coupling of multiple qubits. And in particular, we like it because we build these superconducting circuits on silicon, and at IBM we've got quite a pedigree with silicon fabrication capabilities, and we definitely leverage a lot of the know-how from our silicon past in order to help us design and develop better and better quantum processors with this technology.
How do you even start building these things?
Well, first off, to build a quantum computer, you need qubits, and there are many different places where you can find naturally occurring qubits. So things like the energy levels of atoms, or the energy levels of ions, the spin of an electron. You can spin one way or spin the other way, or even the polarization of a photon. But there's actually other types of qubits that you can artificially make using other materials. So, for example, we can use superconducting metals to make circuits. And it so happens that you can make a particular circuit using an element known as a Josephson junction, and you can make an oscillator. And this oscillator can resonate at a particular frequency and can actually serve as a controllable man-made qubit. Many of them then make up a quantum processor, but for any of them to actually function in a quantum mechanical way, we need to cool them down to extremely low temperatures.
We're not even going to ask how a Josephson junction works, because that's clearly going to lead us down a whole other rabbit hole. But we do want to know why IBM's quantum computer looks like a steampunk chandelier.
So the chandeliers and the steampunk type look that you've seen are actually the refrigeration units that house the quantum processors. And they cool down the quantum processors to just a little bit above absolute zero, so around 10 to 15 millikelvin.
And why does it sound like an asthmatic milk float trying to get over a speed hump?
What you're hearing there is actually a cryocompressor that is part of the cryogenic refrigerator. And it works kind of like a reverse heat pump, and it just helps to move entropy out of the system and cool down the insides of the refrigerator.
Okay, and is it true quantum computers won't work without dental floss?
Yeah, so dental floss is actually one of these materials that we use on the inside of the dilution refrigerators that we have to make sure that things don't move around, and it doesn't thermally short anything. So it's actually a very good kind of inert material for us to use to have some physical clamping of various components and cables inside.
So, quantum computers are made with dental floss cable ties. You heard it here first. If that's not an invitation to scour your bathroom cabinet and see if you can knock up a Rick and Morty portal gun with some cotton buds and empty bubble bath bottles, I don't know what is.
And for a bit of inspiration, why not have a quick listen to what another of IBM's quantum wizards, Dr. Stefan Filipp, told us while we were gawping blankly at IBM Q, marvelling at all its shiny bits and wondering what they did.
My name is Stefan Filipp, and I'm working at IBM Research in Zurich on the experimental realization of quantum computers, improving these machines to actually get to real applications. So I'm excited actually in building a quantum computer, because it's just the mere idea or the vision of building a machine that can give us a solution to a problem that we cannot get otherwise.
And maybe you can talk us through this wonderful contraption.
What you see here is a dilution refrigerator, cooling the qubit down to almost zero temperatures. We are talking about minus 273 degrees Celsius, because we want to avoid any thermal disturbance on the system. So it has different layers. So we are going down from at the top, we are at the 50 Kelvin stage, and reaching then 10 millikelvin at the bottom stage, where we then mount our qubit chip. So you see this copper post, and on this copper post there is a sample holder, we call it, and on this there is this qubit chip, which is basically electronic circuits which are out of superconducting material. So what you have to do then to control our quantum bits, you have to send in microwaves. Microwave pulses that controls the states of individual qubits, but also microwaves for controlling how they interact with each other. And the other thing is then you want to extract information out of the system. You want to know basically what state the qubit is in. And for doing so, you send in another microwave pulse and look at the reflected signal, which then carries the information about the state of the qubit. Measuring you only do at the end. That's one thing that you have to keep in mind whenever you run some algorithm. Otherwise, the quantum information would be gone.
So, as well as the fridge, the pump, the flask of chips, the metal posts and the dental floss, there's also a microwave. It really does sound like something that's been knocked up in a shed by a couple of geeks.
Very much like this podcast, in fact.
So, that's IBM's machine. Now, what about Google's? Well, they've certainly got a good man on the job, Professor John Martinis proved in his graduate thesis way back in the 1980s, when we were just starting to marvel at our newfangled 8-bit microcomputers, that the mysterious Josephson junctions that IBM's Jerry Chow was talking about earlier showed quantum effects. 35 years later, the professor's using these things to make the superconducting qubits in Google's new 72-qubit quantum processor Bristlecone, which was apparently named after a pine tree.
So we wanted to build a system that was around 45 or 50 qubits, and we were just thinking about how to architect that system so that you can do error correction as a totally separate experiment. And then as people were building that, they decided, well, that didn't look very beautiful and had these qubits sticking out of the side, so they just increased the number to 72 so that you had kind of almost a square array to build this in, and it was just kind of a natural size to stop at.
And how are your superconducting qubits different from all the others?
For the qubits we're making, we have an error per operation, like a 2 quantum bit operations, which is the hardest thing to do, of about maybe 1 error every 200 operations or so. But we really want to improve our qubits so that it's 1 error in about 1,000 operations before we can do error correction and do more complex operations. So we have a ways to go, but we think it's within reach and we know things to fix it. Other groups are more like 1 error every 20 to maybe 40 operations, something like that. So we're hoping that our technology and the way that we're doing it has a lower error rate, which are going to enable us to do these complex algorithms a little bit sooner. You know, of course, we have to get it to work and show that everything is working fine, but that's kind of what we're particularly excited about. And as we've built up our systems, we've been showing in some preliminary experiments that this error is not getting worse as we're building up and making more qubits. So that's why we're optimistic that we can get to quantum supremacy in a modest amount of time this year.
Wait a minute, did he just say
quantum supremacy? I think he did. And Google recently dropped Don't Be Evil from its code of conduct. Surely no coincidence.
So, Professor, what is quantum supremacy? It sounds a bit sinister. Had we better start preparing for the enslavement of humanity?
No, that's clearly not what we're thinking about. Supremacy is maybe not the best name. Some people are relabeling this as quantum advantage. What we're trying to do is run a very simple algorithm to show the power of a quantum computer and to show that you can have this kind of exponentially growing quantum processing power, which is the key for the quantum computer. Whereas if we want to check if the algorithm is working properly for our quantum computer that we're building, we would then have to run a classical supercomputer for much longer than the time we would run the quantum computer. So it shows that the quantum computer is solving that problem in a much faster, more efficient way than a huge supercomputer. So that's kind of the thing we're trying to push for right now.
So let's just get this right. You think your Bristlecone chip with its 72 qubits can outstrip a classical supercomputer possibly before the end of this year?
So the algorithm is fairly simple. It's actually not useful for anything. It just all it does is show the power of the quantum computer. Although one might argue that it's useful for actually checking that your quantum computer is working properly. So it's like when you start up your computer, it does a RAM check and maybe checks that the CPU is operating properly, and you could think of it as that. And when we boot up our quantum computer, we want to run a program to make sure that the quantum computer is operating in the way we think it should operate. But in the end, what we want to do here is show that the quantum computer is powerful and check the quantum computer. And then, of course, the next stage is actually going to be doing something useful. And we have the theory team working on that, and that's clearly what we're going to do right after we can get a quantum supremacy experiment to work.
But if you attain
quantum supremacy
or quantum advantage this year, how long do you think it'll be before you'll be able to scale up the machine or get error rates down sufficiently to do some of the really useful stuff that we were talking about earlier?
We actually think we can just kind of brute force scale it up with more or less the technology we have in hand, provided everything works okay, to something like 1,000 qubits or so, which is very interesting from the point of view of running useful algorithms potentially and doing error correction. And, you know, that's going to take, you know, a few years, but not too far in the future. And then past there, we're starting to talk about what we would do to scale up farther to solve complicated quantum chemistry problems. And that would take, we're estimating, something like 1 million qubits. So we're thinking about, well, what do we have to do that? And we have some avenues that we're investigating and working on that. And, you know, to get to 1 million qubits is probably going to take at least 10 years.
So do you think you're going to get there first?
This is not like a horse race where we're trying to beat each other to make this happen. We're really racing against nature. And can someone build something clever enough and, I don't know, trick nature well enough to get this to work? Of course, I think we have a really good approach, and of course everyone thinks their approach has certain advantages, and that's all great. But, you know, we just have to do the research to see if we can get good enough fidelity and low enough error rates and scale up enough qubits to make it work. And I think it's very exciting right now because we see all these different approaches and we try to figure out what's working and why it's working. We know how to make individual qubits and kind of couple them together, but building a full system and scaling it up, I think is going to be a lot harder than people think. And we're figuring it out right now.
As are others in the superconducting qubit fold. In fact, as well as the big boys, a startup called Rigetti Computing already has 16 and 32 qubit quantum computers, and it recently announced that it was working on a 128 qubit machine that should be ready sometime in 2019. It too is hoping to attain quantum supremacy!
Only it calls it quantum advantage, which sounds far less sinister.
Almost cuddly, in fact. I don't hear a Dalek voice in my head now, only Elmo from Sesame Street. Quantum advantage!
There are also a few experimental superconducting quantum computer projects in universities across the globe, including at Oxford.
So let's sum up what we've learned about these emerging quantum computers.
They only work if they've been supercooled to temperatures as cold as deep space.
They're made using qubits that can perplexingly exist in two states at once.
But these qubits are extremely fragile and error-prone.
Nonetheless, the brilliant scientists working on them reckon they can soup up these machines to eventually do things that, to paraphrase Arthur C. Clarke, will be so advanced that they'll be almost indistinguishable from magic.
So, in other words,
they're super cool and fragile things, perplexing in their motions. Even so, some clever so-and-sos have mighty notions. If they get them powered up, they'll work like magic potions. Super cool and fragile things, perplexing in their motions. Super cool and fragile things, perplexing in their motions.
And it appears peculiar and mysterious to everyone.
As we mentioned before, superconducting qubits may be first of the starting blocks, but next time we'll be delving into some of the other bizarre ways people are building qubits and quantum computers.
Oxford University Professor Simon Benjamin's back to explain how Britain has a sporting chance to be first in the race to build a really useful quantum computer,
using small modules networked by light particles.
And Oxford PhD student Vera Schaefer, who's also working on the machine, tells us how they make qubits by trapping and levitating particles of calcium inside a hoover.
A vacuum. Instead of vacuum. We'll also learn how Microsoft hopes to leapfrog the competition and get straight to building a world-changing Uber machine by making error-free qubits using an elusive particle that's only recently been proven to exist.
And we'll find out why we're moving into a new era where quantum computers that don't work properly might still start doing some really amazing stuff, potentially even solving the energy crisis.
And if you're a top quantum computer scientist who's listening to this thinking, they've got this all wrong, or I'm making a better one, then please feel free to get in touch and put us right. You can email hq@stupidqubit.com or tweet us at @stupidqubit.
Ditto if you're writing software for these machines, because in episode 3 we'll be talking quantum programming and meeting the world's first quantum games developer.
As well as a quantum programming banker who used to write hit games for the Commodore 64 in the 80s.
You can check our website stupidqubit.com for links to further information about the people and technologies we've mentioned in this episode.
And thanks to all the scientists who graciously tolerated our ignorant grillings and patiently explained their ideas and experiments to us.
Doctors Jerry Chow and Stefan Filipp from IBM Research, Professor John Martinis at Google, and Professor Simon Benjamin at Oxford University.
And if any of them ends up winning a Nobel Prize, who knows, this podcast could be an important historical document one day.
Or maybe a historical joke if it turns out we're in the parallel universe where Elon Musk was right and we're all part of some alien experimenter's Quantum Truman show.
Thanks to Al Murray, Chris Sciacca of IBM, Hannah Rowlands of Enkit, and Ilyas Khan of Cambridge Quantum Computing, who we'll be talking to in an upcoming episode.
And love and thanks to our long-suffering families for tolerating our endless hours in the virtual shed putting this podcast together. Thanks Lisa, Ellen, George,
Nadia, Samuel and Michael.
And sorry we didn't get this episode out quite as quickly as we would have liked, but we are literally doing it all ourselves at home while trying to juggle it with work that pays the bills. We'll get the next one out as soon as we can. It's half scripted already, but do bear with us.
Thanks for listening, and if you enjoyed this podcast, please tweet it out, share it on Facebook, tell your friends, like, subscribe, and all that nonsense.
We'll probably get round to crowdfunding and hawking merch sometime in the future if there's a demand for more of these, but for now it'd just be nice to know it wasn't a totally wasted endeavour. So do get in touch, tweet us, tell us what you thought about it, tell us how we could improve it.
And surely some people are as fascinated by all this stuff as we are.
And if you're looking for anyone to make sense of it, remember we're always open to journalistic, broadcast or other paid gigs that might help placate our wives after working most of the summer for nothing on something that no one understands.
Shameless plug over. That's it. See you next time. And remember, don't have nightmares.
Especially ones about
quantum supremacy!
Qubit.